Okay, we're still in chapter 3. This section is going to talk about the addition rule. So it says two events A and B are mutually exclusive. Mutually exclusive when A and B cannot occur at the same time. That is, A and B have no outcomes in common. So if you look at these as Venn diagrams, A and B are totally independent of each other versus having some shared components, which is this little piece in the middle. So we would say that this one is mutually exclusive. Nothing is shared in common. So how do we recognize that? Well, let's see. Determine whether the following events are mutually exclusive and explain your reasoning. So event A says that we're going to roll a 3 on the die, and then event B says that we're going to roll a 4 on the die. So are these mutually exclusive? And the answer in this case would be yes. They are mutually exclusive. And the reason is because you cannot get a 3 and a 4 at the same time. So when you roll the die, you either get a 3, and you roll it again, you get a 4, but you're never going to get them both at the same time. Number 2, randomly selecting a male student and randomly selecting a nursing student. These then, this would not be mutually exclusive. And the reason they are not mutually exclusive is because you can have a male nursing student. There's nothing that says you cannot have a male nursing student. So randomly selecting that would not be mutually exclusive. Example 3, randomly selecting a blood donor of type O blood, randomly selecting a female blood donor. Again, this would not be mutually exclusive. And the reason there is because, again, you can have a female with type O blood. Type O blood is not exclusive with just males. Some females also have type O. So now we actually get to the rule, the actual multiplication rule. So the multiplication rule says that events A or B occur, says the probability of A or B, so notice the word or, is given by the following formula. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which this probability of A and B is what they share in common. So we're going to subtract those out because we don't want to count them twice. They're going to be counted in either probability of A or the probability of B, so we have to take out that piece that's in the center. If they are mutually exclusive, then there is no piece in the center. So again, if we go up to the picture, you can see that there is an actual piece here in the center. And this piece in the center is what we're going to subtract out. This is the probability of A and B. that little piece is. So that's the little piece we have to subtract out. We already counted it in one of the two, so we have to subtract it out. But if they're mutually exclusive, they have nothing to subtract out because there's nothing common. Okay. All right, so let's do some examples. Hopefully this will be clearer. So you select a card from a standard deck. What is the probability that the card is a 4 or an ace? So probability that we get a 4 or an ace. So that says we're going to find the probability that it's a 4 minus the probability that it's an ace. Oops, so plus the probability it's an ace minus the probability that we have a 4 and an ace. So by now you may be saying to yourself, but there's no way if I'm only selecting one card that one card can be a 4 and an ace. And you would be absolutely right. That one card cannot be a 4 or an ace. And so that's why this doesn't exist, making this problem mutually exclusive. Sometimes you may not know whether they're mutually exclusive until you actually read the entire question or put the whole thing to making sense. So the probability that you select a 4, well, there's 4 4s out of 52 cards. The probability that you select an ace, there's 4 aces out of 52 cards. Again, you cannot have a 4 and an ace at the same time. So if I add these together, I have 8 over 52, which is going to be approximately equal to 0.154. So about 15% of the time you could select randomly 4 or an ace. All right, problem 2 says, you select a card from a random deck. What is the probability that that card is a 4 or a club? So again, if we look at our formula, that would say we have the probability that we're going to select a 4 or a club. I write that in the full definition. That would be the probability that I get a 4 plus the probability that I get a club minus the probability that I have a 4 and a club. Well, now you have to ask yourself, in this deck of cards, is there a 4 of clubs? And the answer to that is yes, there is a 4 of clubs. So how many 4s do we have? We have 4 out of 52. How many clubs do we have? Well, there's 13 clubs. So that's 13 out of 52 minus, well, out of those 13 clubs, one of them is the 4 of clubs. So we have to take out the one that is the 4 of clubs to get my answer. So that would now be 7 out of 52, which is approximately, I'm sorry, I added correctly. It'd be 7. I'm not sure where that came from. It would be 17 minus 1, which is 16 out of 52, which is approximately 0.308. So more chance that you would get a 4 or a club than a 4 or an ace. Example 3, you roll a die, find the probability of rolling a number less than 3 or rolling an odd number. So probability that we have less than 3 or an odd number. So this would be probability. Now probability of less than 3 would be a 1 or a 2 plus the probability that I have an odd number. Well, an odd number would be the 1, the 3, and the 5 minus the probability of the fact that it's less than 3 and odd, which you might recognize by the way I've written it out this time, that this 1 appears in both lists. So I have to take that one out. So this would be, well, if I'm going to have a number less than 3, that would be the 1 or the 2. So that's 2 out of 6. Plus an odd number, well, there's 3 odd numbers on the die, so that would be 3 out of 6. Minus, again, I have to take out the 1 they share in common, or the item they share in common, which in this case happens to be the number 1. So that's minus 1/6. So 2 plus 3 minus 1 would be 4/6. 4/6 is approximately equal to 0.667. All right, so another example. The frequency below, or to the right, shows the volume of sales in dollars and the number of months in which the sales rep reached that level in the past 3 years. Using the sales pattern, find the probability that the sales representative will sell between these two numbers. So it's the probability that they sell between 75 and 124. So that would be this category and this category. So if I call this event A and this event B, so the probability of A or B would be, again, the probability of A plus the probability of B minus the probability of what they share in common. And again, you should be able to see that the numbers aren't going to be in both. The number of months can't be in both categories. You either sell between 75 and 99,999 or between 100. There's no way that that's going to be in both categories. So we could say then that because we know these are mutually exclusive, this part cannot exist. And the probability of A then would be 7 out of, well, how many months is this? It tells us that there are 3 years. Be careful, this is in months. I could also add this up, and that would be 36 months. So 7 out of 36 plus 9 out of 36. So 16 out of 36, which is approximately equal to 0.447. And it makes sense that about half the time he was in that target area anyway. So about half the time, that's where he should reach. Right. Using the addition rule to find probabilities. So another example, a blood bank catalogs the types of blood, including whether they're Rh positive or Rh negative, given by the donors in the last 5 days. Find the probability that the donor has type O blood or type A blood. Well, this should make sense that a donor cannot have type O and type A. It's one or the other. So this one is just going to be the probability of O plus the probability of A. There is nothing to subtract off here because you cannot have both type A and type O. So if I look at my chart, which happens to be on the next page, so type A, there are 164 type A. There are 184 type B out of a total of 409 people. So that would be equal to 184 out of 409 plus 164 out of 409 which is equal to 348 out of 409, which is approximately equal to 0.851. So most of the people that have donated blood in the last month, according to this chart, were either type O or type A. Find the probability that the donor is type B or Rh negative. So B or Rh negative. Can you have a person who is B and Rh negative? And the answer to that would be yes. So we're going to look at the probability of B plus the probability of an Rh negative minus the probability of a B Rh negative person. So we have to take out the ones that we're not going to repeat. So probability of type B, there are 45 people. Rh negative, there are 65 people. But of those 65 people, some are type B, so that's why we have to make sure we take out the ones that are type B. And in fact, there are 88 type B negative people. So type B negative people, there are 8. So the probability of B would be 45 out of 409, still 409 people, plus 65 out of 409, minus the 8 people that are Rh negative and B type, so minus 8 out of 409. Add and subtract all of that, we get 102 out of 409, which is approximately equal to 0.249. Again, make sure you're rounding to the correct decimal point when it asks. Oftentimes 3 decimal points is common, so make sure you're reading carefully and rounding correctly. All right, so this next example is going to be about combining different rules to find probabilities. So again, so much of this chapter is in how we read the problem. So be sure that you are really reading carefully so that we can figure out what we're trying to come up with. So find the figure, use the figure to find the probability that randomly selected draft picks are not a running back or a wide receiver. So not a running back or a wide receiver. So let's say event A would be that a running back is chosen. And event B would be that we choose a wide receiver. So we want the probability of A or B. Now you may be saying, wait, I don't want the probability of A or B. I really want the probability that it's not A or B. So probability that it is not A or B is absolutely what we're looking at. But remember, sometimes it's easier to find the probability of what is versus the probability of what is not. So let's find the probability of what is first. So that would be the probability of A plus the probability of B minus the probability of A and B. Now let's make sure on this list that none of these rookies were both running backs or wide receivers. And if you look on here, here's the running backs. There's 23 running backs. Wide receivers are on this side. There's 31 wide receivers. But there is no person who plays the running back and wide receiver position. And that would be more common in the NFL than it would be maybe in Pee Wee football, where they do have dual roles. But at this point in time, the only draft picks were either wide receivers or running backs. So the probability of a running back in that day, probability of a running back, there were 23 running backs out of, so how many total positions were there? The total positions, I almost covered it up, was 253. So it's 253 plus the wide receivers, and there were 31 wide receivers, 253 total. There's none that they share in common. So that would be 54 out of 253, which is approximately 0.213. So again, that's the probability that we get one of those positions. So the probability that we don't get one of those positions would be 1 minus the probability that we did get it, which we just figured out. So that's 1 minus 0.213, which again is approximately 0.787. So several different rules combined there. The combining of the or statement and the combining of the complement. So be sure that you, again, read very carefully and don't hesitate to do the correct one versus the incorrect one and then subtract it. And that wraps up section 3.